So I'm Zilong, and I'm from the data infra team of the ByteDance. And we also deliver many data infrastructures for our products like TikTok and CapCut. So the title is about the data management and the model training. But my co-speaker, who is responsible for the training part, could not come here today, unfortunately. So our session will focus more on the data side. And it's also my first English presentation, so I hope it will be fine. So here's what we will cover for today's session. For the data management section, I will introduce how we built the EB scale feature store based on the Magnus Lake, which is our internal version of the Iceberg. And then I'm going to introduce how we evolved the Max Lake to be an all-in-one data management solution for the large model training. And for the training section, I will introduce how we supported efficient large model training on the large-scale datasets based on the ByteDance Streaming and the Max Lake. So ByteDance Streaming is also our internal version of the Mosaic Streaming with a lot of optimizations. So let's go to the data management. So before we dive in, I'd like to share some context first. So a training sample is composed of many, many features and some labels. A feature could be very easy, like the age, job, and gender. Well, it could also be pretty complex. And at that case, we might have to do some complex computation based on the external data sources or the existing feature values from the feature store. And the labels will contain some actions from the user. So given the sample, the model can learn that a user with these sort of features has done the actions within the labels. So here is a simplified offline machine learning workflow for a predication system, which is extensively used in our many business like recommendation or advertising and searching. So a user action will request the predicate service for some results, like a rank list of some content, and it will generate the labels of this request. And the predicate service will also dump the required features for this user according to the configurations set by algorithm engineers. And then a join service will join the labels and the features to produce a training sample, and finally write it into the feature store. So after a period of accumulation, algorithm engineer will select some features and labels to train new models. And if the model is verified to be OK, it will be deployed to the online predicate services. But there is actually a problem in this picture, is that if I want to use a new feature to train models, I have to wait for the feature store to accumulate enough samples containing this feature. And the time depends on how many samples I need and the frequency of the online requests. So I will talk more about this in the next page. So our early solution was based on the row store, and the data was stored as raw HDFS files. So this way was proved to be very bad because it doesn't support column projection. So we have to read all the features, even though we only need some of them. And since row store is not very good at compressing the data, this will cause additional storage overhead. And as we talked on the previous page, to backfill or correct the feature, we must rewrite the whole data. So we summarize some points that we need for a good feature store. First, we should be able to perform update and query operations just on some of the columns. And the data should be versioned and could be accessed and modified independently without any storage cost. And finally, we should be able to write and read the data through both streaming and batch engines, such as Blink and Spark. So we plan to build our next generation feature store based on the data lake. And we choose Iceberg for its hierarchy design of metadata, and which is great for our cases. And At that time, Iceberg has good support for both Flink and Spark engines, which was also a big win. So is Iceberg just enough for a good feature store? At that time, the answer should be no, because at ByteDance, our largest feature store has up to tens of thousands of features, and is still growing. But Iceberg can only do updates by copy on write or delete and insert, and both of them will rewrite the whole record, while an efficient column level update based on the column value merge on read was a must-have for feature store. Also, it will be better if we can customize the merge on read strategy and have better merge on read performance. So this led us to build Magnus Lake, which is an enhanced version of Iceberg. And it is especially for the large-scale machine learning workloads. And now it is storing more than 5 exabytes of the data and has powered the feature store across ByteDance over the past few years. So first, let me talk about the implementation of the column level updates. So Magnus supports both positional updates and equality-based updates. Positional update is designed for read, modify, write operations, because when we read the data, we can get the position of every modified record so that we can avoid doing merge on read by the key column when reading the data. And equality update is designed for write-only operations where the changes may come from the external sources, and the updates are not based on their columns, on other columns in this table. In this case, we can write down the update files directly. And Magnus also supports customizable merge on read strategies, so that user can write their own merge on read logic to meet their business requirements. And for example, I want to add an action to the labels of a user. I can just use the concat to list strategy to do the update, just like the update file with sequence number 4 in this picture. You can see in the right corner. So now we have a good merge on read based column level update. But how do we ensure the read performance? So one problem is that there might be too many update files to be merged, since there are so many features being added, and this can cause performance issues when we read the data. But actually, in our scenario, the features are added by different users, and every user just read their own features. So after pruning the update files based on the required columns, there won't be too many files to be merged within the single scan task. But this situation does exist where the user has added many features with complex merge on read logic, and he just wants to read all of them. Then here comes Arrow Engine. So Arrow Engine is built in C++, and we have column-wise merge on read. And we also have done a lot of optimizations to get better read performance. So for example, the merging of the columns are parallelized to better scale on the multiple core CPUs. And Arrow Engine is also a middle layer for us to support different engines and file formats. So I'll talk about this in the next page. So as you can see in this picture, there are lots of engines need to be supported, such as Spark, Flink, and Ray. And Byted Streaming is our internal version of Mosaic Streaming. And Krypton is our self-developed hybrid searching and analytical engine. And Premise is our self-developed training system. So they are all delivered by our data infra team. And we also have lots of different file formats to support, such as Parquet, RIPC, or TF record, and so on. So our solution is to define an abstract read-write interface based on the Arrow in-memory format. So any new file format only needs to implement its own read-write interface to get supported in Magnus Lake. And then we wrap the scan task and writing interface for different languages so that a new engine could also be easily supported by just integrating with the language SDK. Yeah, and we also find that the community has also raised an issue earlier this year, which was trying to make it easier to support new file formats. And yeah, it's implemented in a different way, but I think I think it will be a very exciting and useful feature. And of course, compaction is definitely needed for better read performance. So Magnus has its own catalog service and table maintenance service. For the catalog service, it has a backend with some MySQL RDS instances, and it's managing more than 72,000 of the Magnus tables stored in the HDFS or object stores. And it provides RESTful API externally for the CRUD operations on the Magnus tables. And the permission control is realized by reusing the existing permission control from the HDF directory or object stores, so that once the user gets the read-write permission of the HDF directory, they get the read-write permission of the Magnus table. So for the table maintenance, we have some background tasks scheduled regularly to check the table health, and some of them will trigger some new tasks to build indices or caches, and also do the compaction for the table, both for the data and the metadata. Yeah. Okay, let's take a look at the feature engineering practice with Magnus Lake. So first is the feature analysis scenario. So every algorithm engineer could check out a new branch where he can backfill the features he wants to analyze. And during the training, only the required features are read. So the benefit is that features are perfectly isolated among different branches without any storage overhead. And there won't be any read implications when loading the features as well. So another scenario is also very straightforward, is that we can reuse all the features on the master branch without any storage overhead for every model's training. So compared to the traditional row store design, we have more than 90% of the storage saving in some of the production cases, and that's an incredible number. Okay, so that's all for the feature store. And let's move to the large models next. So the first thing is that, very surprisingly, we found that many requirements from the large model training are very similar to the feature store. So for example, for the data labeling scenario, we might prepare some data sets. Then we repeat the labeling training process to iterate many models on different versions of the data. So this is just like the feature engineering workflow, which also requires efficient column-level updates and merge-on-read mechanism. And large model training also has massive and complex data sets with a bunch of versions to manage. For pre-training, SFT, RL, RM, and evaluation, even the checkpoint files. And all of them need a good versioning mechanism and support for different file formats. And of course, so many datasets from so many scenarios require different engines to read and write, so, which is also very similar to the feature store. So other than that, we also have some new requirements from the large model training. Basically, we need a platform with better UI UX for tracking tables, previewing the data and doing table migration across data centers or storage mediums. For example, we usually have much more storage resources than computing resources. And in this case, we need to move the data to the data center that has more free computing resources. And we also need the capability to adjust storage replicas of different parts of the table to maximize the utilization of remote storage bandwidth and solve the read hotspot issues. So, and for existing data sets, such as some open source data sets that we want to use them directly, we can create register table by scanning the existing data set and generate Iceberg metadata files under the metadata path of the table. And finally, for better data insight and troubleshooting experiences, we might need the real-time OLAP engine and the search engine. So I'm going to introduce this later in detail. So first, let me show you the one-stop machine learning platform built with our machine learning infra colleagues. So as you can see in this picture, we can preview the detailed information of the table, such as the file number, the total storage volume, the record number, and the schema of the table. So all of them are collected from the Iceberg metadata and cached in our table maintenance service. So for the table maintenance, administrator can see the detailed metrics of all the tasks for a table and manage the task execution as well. So the user could trigger certain type of tasks like the table migration, cache creation, and so on through the platform interface. So for the data insight and troubleshooting, we also integrated a crypto engine to query the Magnus table directly without re-ingesting the data to the OLAP engines. And it also has some important optimizations, such as the predicate pushdown and data caching on the external Magnus table to get optimal query performance. So the next thing I'd like to talk about is how we get the search ability on the Magnus Lake. So for the better experience of search queries, such as full-text searching, we hope they can finish in a few seconds to be usable for the business. But unfortunately, Iceberg is designed for the batch query. So we have to duplicate the data to other search engines like Elasticsearch to get better performance. And this will make the data hard to manage and cause additional storage cost. So our solution is based on the fact that every data files in the Iceberg table will become immutable once they are committed. So we can create index files alongside them with a 1-1 mapping. So during a search query, for every file scan task, we can read the index file first to get the row indices, then use the row indices to read the data file. And for top K queries, such as the vector search, we have to do a global sort merge operation to get the final result. And as for the full-text indexing library, we cannot use the Lucene because our reader is implemented by pure C++. And after some investigations, we choose Tantivy as our full-text index kernel. Since Tantivy is a Rust library, we integrated it with the arrow engine through the foreign function interface. And the index searching logics are completely implemented in arrow engine so that different engines could reuse the index searching ability by integrating with arrow engine through the language bindings like PyBind for Python or shared library linkage like C++. So we made a benchmark on a text data set, which was picked from the real data sets used for our large language model pre-training. So this data set has about 4 TB of the data with about 20,000 data files. And the result shows that the first query can be finished at the second level. And the following queries can be finished at the millisecond level while the data caching is used. So the vector index on Magnus Lake is already in the testing phase. And we have also opened a proposal in the community to support full-text index and the vector index on the Iceberg. So here's the issue. OK, let's bring them all together. And so as we can see in this picture, the whole life cycle of the large model training is included in the top box. And the read and write operations to the different data in the bottom box are finished by interacting with our engines, SDKs, REST APIs, and so on. And this sort of stuff will interact with the arrow engine, and the arrow engine will read and write the dataset directly, just as shown in the picture. Okay, let's move to the model training section quickly. So I think our machine learning infra colleagues have started using the streaming since early in the last year, and we choose Mosaic Streaming as the basis to build our next generation data loader called ByteDance Streaming for these several advantages. But ByteDance Streaming has two design decisions, which is different from Mosaic Streaming. So firstly, ByteDance Streaming choose to read the shards from remote storage directly into the memory. Because in our environment, the disk resources are not sufficient enough to store the shard files all in the disk, because our source scale is extremely large. And also, the disk failure is always happening. And what makes it worse is that the disk space can be easily taken up by other apps, such as log files or codedump files. So for these reasons, we don't rely on the local disk. And the other one is about the elastic deterministic. So I think it's a very useful ability to enable the same sample order when the parallel configurations change. But still, if we don't re-download the shard files to the local, this will be problematic, and I will talk about it in the next page. So as we can see in the middle of this picture, there are a bunch of shards which are already shuffled. And in Mosaic Streaming, even the data parallel size or worker number changed. The global sample order will not change because the consuming order of the shards didn't change. And while the problem is that all the workers might be trying to read the same shard, but only requiring a small piece of the shards, and this can cause severe read hotspots and amplifications. And but in ByteDance Streaming, every worker will start reading from the dashed lines in the picture and consuming the shards sequentially. So there won't be too many overlaps. Basically, it's just at most one shard between every workers. And the read amplification can also be reduced since the worker would read the whole shard from the start to the end instead of just small pieces. So we have also made a lot of optimizations to the streaming itself. And here I will briefly introduce three of them. So first, we implemented a multi-source dataset, which contains several datasets mixed in proportion. So the mixing strategy could be adjusted during the training process. And in every batch, the data from all the sources will be included according to the mixing proportion. But in Mosaic Streaming, I think a streaming dataset will only contain the data from a single stream within a batch, because they belongs to the same single shard space. And the second is that the lazy sample ID generator. So in Mosaic Streaming, every sample will be assigned with the sample ID during initialization. But when dealing with large-scale datasets, this would cause memory issues. So we implemented ID generator mechanism to lazily generate sample IDs for the samples. When they are and when they are actually accessed, it will generate the IDs. So it also supports the reshard scenario. And finally, we have a broadcast prefetcher. So it's based on shared memory and make it possible to reusing the same samples across different training processes in the physical node. And it also supports GPU prefetch, which can avoid data movement between the CPU memory and the GPU memory. So now we can try to integrate ByteDance Streaming with the Magnus Lake. So ByteDance Streaming can support any formats by simply implementing the corresponding format reader. And I think it only takes 100 lines of code under the format directory. As we can see in this picture, the Magnus reader supports two types of sample access modes. So for the datasets where a single shard is relatively small, such as some short text datasets, we can load the whole shard into the memory from the remote storage. So the subsequent accesses of the sample could be performed randomly based on the shuffle result. And for datasets where a shard is very huge, like video datasets, we can consume the shard rows by rows so that only a few rows of the shard will be resident in the memory. So this actually trades randomness and throughput for better memory efficiency. So why didn't use MDS directly, as it should be well optimized for the training workload? So I think the most problematic thing of MDS is that we have to duplicate the data just for the training, while the MDS is a row store and it's not very good at the compression. So the storage cost will be much higher than we thought. And then it's not very easy to update the MDS datasets. So we have to rewrite the whole datasets to just update a single field, and this is normal for a row store. So the concept in the MDS could be mapped to the Iceberg. So a dataset is a mixture of Iceberg tables. A stream is an Iceberg table, and a shard is a piece of Iceberg table. While it could be like a file or a row group, and or even like any arbitrary ranges of the file. So and the index.json file of MDS is also similar to the hierarchy metadata of the Iceberg, where we can get the information of every shards in this table. This is so here's the process of like ByteDance Streaming reading from the Magnus table. So the multi-source dataset is the mixture of some ByteDance datasets, which is our internal version of the streaming dataset. And ByteDance dataset, similar to the streaming dataset, will contain multiple ByteDance streams. And a ByteDance stream is just equal to a Magnus table. So we can get the shards of the stream by planning file scan tasks from the Magnus table, then wrap them to be the shards objects of the streaming. So if the shard is at the row group level rather than file level, the row group scan task will have a pointer to the original file scan task together with the row group index and the record count of the row group. And these informations are used for sharding and shuffling in the next processes. So during the planning, we need to go through the Iceberg planning process and initialize all the file scan task objects for the Magnus table, and then construct all the row group scan task objects, and finally construct all the shard objects for streaming. And during read, we will read through the row group scan task to access a shard. So there is actually some problems here. So because we have to construct all the file scan tasks and the row group scan task objects at the initialization phase, so the startup time will be pretty long, and the memory usage will be extremely high in the case we have ultra number of sources. And this is just similar to the sample ID generation we have talked before. So our solution is to just build plan cache asynchronously. So if a snapshot of a table is accessed for the first time, we will schedule a task for building the plan cache for this table. And the content of the cache file is serialized from the Magnus scan context object, which has a list of bytes, which representing the serialized file scan task objects. So, and there is also some empty slots for the deserialized file scan tasks, and together with some NumPy arrays, which is compressed representations of the row group scan tasks. So for a single table during planning, we don't have to construct any file scan task objects. And the row group scan tasks are represented by some NumPy arrays, which also don't have the overhead of Python object header. And only when we actually access a certain row group scan task, we construct the pointed file scan task, if not constructed yet. And then constructed the row group scan task with the compressed information from the NumPy arrays. So that extremely reduced the startup time during the training. And so our team was also actively working with the machine learning infra team to build the next generation data loader with Ray and ByteDance Streaming. So this solution can scale ultra number of data sources in the large model training. And we're also considering open source the ByteDance Streaming as well as this solution in the future. And also for the ByteDance Streaming and the Max Lake, we are also considering participate more in the community and try to contribute some useful features to the open source. Okay, that's all for my session. Thank you so much. Okay.